We're going to continue our coverage of advanced Java completable future features by introducing completion stage methods, which are really some of the most interesting features that are part of the completable future framework. And these completion stage methods chain actions together using the Fluent interface pattern to perform asynchronous result processing and composition of results. So a completable future can do various things. We saw before how it can be used in a basic way based on the fact that it implements the future interface, but it also can serve as a completion stage for asynchronous result processing. And the way it does that is by implementing the completion stage interface, which you can see here. I actually strongly recommend you take a look at the documentation for completion stage because it does a really nice job of explaining the various methods we're about to cover here. So what is a completion stage? A completion stage is a dependent action that runs after the completion of an asynchronous call, and it handles the result of said asynchronous call. So when an asynchronous call completes, then a completion stage method will be used to perform an action that depends on the result from the completed asynchronous operation, which is a bit of a mouthful, but it describes what's going on. And we'll take a look at an example here to make it more clear. This example, as always, can be found in my GitHub repository, this time in the EX8 folder. So what we're going to do is we're going to go ahead and create an unreduced big fraction. So you can see here that we're going to use the value of factory method. We're going to pass in a numerator, which is a large big integer, and a denominator, which is another large big integer. And we're going to pass in the flag false to indicate not to reduce that big fraction. And as you know, reduction is basically trying to get it down to essentially its most concise form. So once we have that unreduced big fraction, we're then going to make ourselves a supplier variable called reduce. And that supplier variable is going to go ahead and reduce the unreduced big fraction. But of course, it's not going to do it at point of call here. It's not going to do it where we define the reduce variable. Instead, that's just defining a lambda variable, and then we're going to use that in the context of an asynchronous factory method. So we're going to say CompletableFuture.supply async, which calls the supply async factory method. We looked at the implementation of that in a previous lesson. And it's going to pass in the reduce action, which in this case is a supplier. And what that'll do is that'll go ahead and call big fraction.reduce on the unreduced variable in a background thread. So action, the supply async call will take the reduce action, which is a supplier, and then it'll go ahead and arrange to run that reduce action in a background thread from the common fork join pool, kind of as we talked about before. When that call is finished, when we're done with asynchronous processing to reduce the big fraction, then the dependent action, the dependent completion stage method, then apply is going to be called with the dependent action. And the dependent action here is to go ahead and convert the reduced big fraction from its improper form into its mixed string form. So that'll convert that big fraction into a mixed string. And then we can actually chain these things together fluently using the Fluent interface pattern, and we'll see this over and over again. And what we're going to do then is we're going to take the string that came from then apply, and we're then going to invoke the then accept completion stage method, which will have the action of printing the mixed string out on the standard output. And you can see we get that by giving the println method reference here, system.out : println. So see, you'll notice what's happening is we're chaining these things together, and I'll talk more about that in a second. So each of these methods, supply async, then apply, then accept, registers a lambda action to apply. So it's actually registering a functional interface, something that conforms to a functional interface, but it's an action which is either a lambda or a method reference. So it registers those things. A lambda action is only called after the previous stage completes successfully. So in order for then apply to be called and its lambda action to be called, supply async has got to finish. In order for then accept to be called, then apply has to finish, and so on. So you can kind of see a transitive closure of dependent actions being chained together here in this pipeline. And this is what we mean when we talk about chaining. So when we chain things together, it's a fluent set of calls that occur one after another as the previous operations complete. So you can basically think about these actions that are being registered here as being deferred until the previous stage completes and a thread from the common fork join pool is available. And we'll see that there's a whole bunch of subtleties here in terms of how that all works, but that's the basic idea of registering these actions. Fluent chaining for completable futures is really cool because it allows asynchronous programming to look very much like synchronous programming. It looks at some level like these calls are being called synchronously, even though they're not really being called synchronously. They're being called in reaction to the completion of previously running asynchronous operations. So it's a cool way of giving you a synchronous programming facade atop what is inherently an asynchronous processing pipeline, which is kind of neat. Using completion stages is done to avoid blocking the caller thread or the original caller thread, the initiating caller thread, until the result must be obtained. So the idea we're going to do here is we're going to set the wheels in motion by using these factory methods like supply async that will start computations running asynchronously. The calling thread or the caller thread, the one that invokes the supply async call, doesn't need to wait around for the completions to finish. It can go on its merry way and do whatever it feels like. You should try to avoid calling join or get. You're very rarely going to use get with completable futures. You're most likely to use join. But if you were to choose to use get with all of its checked exception madness, you want to try to avoid using get or join unless you absolutely have no other option. And usually that occurs at the end of chains of calls that cannot continue asynchronously until you get a result. Why is this a good thing? Why do you want to do this? You want to do this because it improves responsiveness by not blocking the caller thread. The caller thread can go off and do other things like interact with the user or pitch in and perform other computations without impeding responsiveness. Clients and servers that apply this type of approach, which is typically called the asynchronous completion token pattern, which you can read about here. It's from the Posted 2 book, which I wrote about 20 years ago. This allows avoiding blocking completely. You can just avoid blocking altogether, which is really cool. A completable future can serve as a completion stage for asynchronous result processing. And here are some of the methods. There's many, many, many methods here, just a handful of them. Then apply, then accept, then combine, then compose. And there's a gaggle more of these things we'll cover later. When I think about completion stage methods, the mental model that comes in my mind is juggling. And if you think about juggling, if you've ever juggled, if you've ever watched somebody juggle, the whole idea is to try to keep as many balls in the air as possible and only actually touch the ball long enough to transfer it from one hand to the other or to throw it back up if you're doing one-handed juggling. But you don't keep the balls in your hand very long. You just keep them there long enough to throw them up again. And that's what's going on with asynchronous processing. You want to be able to do asynchronous processing without blocking, and you only block long enough, you only handle the results when you're done with the computation. And if things go well, you often initiate the next computation asynchronously. So you basically keep the balls in the air, if you will. You keep everything running asynchronously as much as possible. And the reason why you want to do this is you only want to consume resources when an action runs, thereby reducing system overhead. In contrast, if you block, you are consuming system overhead in some sense. You're consuming system resources by just sitting there blocking. And that's keeping other things from making forward progress. Even though you're parked, there's an overhead for parking and unparking and blocking and impeding stuff, and you reduce the potential parallelism on the system, the inherent parallelism on the system, and so on. A nice metaphor for that are these newfangled cars, which when you come to a stop sign or you come to a red light, the car shuts off, which is very disconcerting at first. If you've ever driven one of these cars, you come up, you're driving along, you hear the purr of the engine, and you come to a stop sign, and then there's silence. And then when you start up again, the car starts up. When you hit the accelerator, it starts up again. But basically the same idea. You don't want to consume resources when you're not doing anything useful. Those types of cars are also somewhat treacherous for pedestrians, because if you're listening for the sound of a car to inform you that there's a car that you're about to be run over by, you'll be fooled because there will be no noise. But you just have to look around. You can't just look in your phone. You have to look around when you get to an intersection. So that's the end of the introduction to completion stage methods. We will talk a lot more about the many variants of completion stage methods because there's literally dozens of these things. But I just wanted to give you the big picture view. The big picture view is to avoid blocking as much as possible by keeping computations running asynchronously and only blocking long enough to handle the results of previously invoked asynchronous calls and then restart them again and do some more work in the background.